Hello everyone, I am Vikas Chandan, a senior research scientist at the Pacific Northwest National Lab, and the work that I am going to present today is joint work done with my collaborator, Professor Aritra Dasgupta, at the New Jersey Institute of Technology, his student, Akshith, Reddy, Kandakatla, my colleagues at PNL, Soumya, Kundu, and Chris Cook, and also Indrasis Chakraborty, who is at the Lawrence Livermore National Lab. So through this interdisciplinary collaboration, our effort is to fulfill the need for adopting data-driven predictive modeling in the energy sciences domain through the use of trust-augmented visual analytics. And what I intend to provide you is a domain scientist's perspective of what we need from the visual analytics community for my domain, and also some of the work that we have actually started pursuing together with Aritra and the team. So at a high level, energy modeling consists of a couple of main aspects. So firstly, understanding the demand and accordingly adjusting the supply. Okay. So this involves ingesting heterogeneous data in the complex models, which are traditionally physics-based models, for informing consumption patterns at the level of the building or at the grid level. And accurate modeling is imperative for an operational infrastructure, and also has important implications for adopting renewable energy in the not so distant future as the main source of energy, right? So this kind of sets the stage for our domain of interest here. Now what we do in this talk is I'm going to highlight two broad groups of stakeholders in this domain. So firstly, energy modelers who have knowledge of data science and are trying to accurately capture the physical processes and combine them with the available data to make predictions. And the other group of stakeholders is building and grid operators who are not so trained in data science methods, but they essentially consume the outcomes of the predictive models that the data scientists generate for decision-making purposes. Okay. So what my talk will do is it will touch upon three interesting aspects. So the need for data-driven modeling, the trust gaps owing to the familiarity of experts with traditional physics-based models, and the role of visual analytics to bridge this trust gap. So let me now talk about the prediction problems that exist in the building energy domain. So when we look at data that comes in from a building, data can typically be categorized into four different bins. So we have controls, which correspond to knobs that can be changed, such as set point temperatures. Then we have exogenous inputs. Those correspond to things which cannot be changed, for example, the outside weather. Then we have measurements, which refers to quantities that are of interest, but we are not trying to maximize or minimize them. So those could be things like indoor zone temperatures. And lastly, we have a category called consumption, which refers to quantities that are of interest for minimization or maximization. For example, the whole building energy consumption. So in a typical prediction setup, we try to predict the measurements and the consumption as a function of controls and exogenous inputs. So the prediction outputs correspond to controls and exogenous inputs, and the prediction outputs correspond to measurements and consumption. And then the use cases, which typically correspond to minimizing the energy consumption or the cost of energy, can be stated as an optimization problem, where the objective function is stated in terms of the consumption variables, and the decision variables correspond to these control knobs. And the exogenous inputs and measurements typically come in as constraints in the optimization formulation. And those could be equality constraints as well as inequality constraints driven by considerations such as occupant comfort, safety, and reliability. Here is a list of various stakeholders interested in this problem space. So we have building operators who are interested in minimizing costs and the cost of energy, but also they want to make sure that there is minimal number of complaints from occupants. The utility company which serves the building seeks to minimize peak demand because peak demand is a high peak demand can result in uneconomical operation of the grid, and they also want to maximize flexibility because they want to utilize buildings for providing grid services such as demand response. Policymakers care about setting codes for how to operate buildings and also making sure that those codes are being followed to the maximum possible extent. Occupants, who are people who live and work in the buildings, they care most about their comfort. So the objective is to maximize comfort. And the scientific community, in this case consisting of modelers and researchers, cares about maximizing the accuracy of energy prediction. So essentially making sure that the prediction problem presented in the previous slide is well formulated and is reasonably addressed. So one thing to note here is that the objectives of different stakeholders can sometimes be conflicting. For example, the need to maximize comfort can directly influence our ability to minimize energy. Usually higher comfort means higher energy, and that would interfere with the building operator's goal of minimizing the energy consumption. So where does data come into this domain? That's what is explained in this slide. So for the prediction problem that was discussed earlier, the traditional approach is to use physics-based approaches. For example, there is a tool called Energy Plus, which is very widely used in this domain. One of the challenges with physics-based approaches, in particular Energy Plus, is that it requires detailed knowledge about the building, such as material properties, wall thicknesses, and so on. And it's very difficult, time-consuming, and resource-intensive to gather all that information. And experience has shown that even after all that information is available, the accuracy of these models tend to be limited. So there is therefore naturally a drift towards using data-driven techniques for these kind of prediction problems. And that is supported by the need, the availability of data today from buildings, especially because of the penetration of building automation systems. The niche need, I would say here, is to convert the data that is available from buildings and that is widely available to building operators into actionable information that the building operators can use to address different stakeholder needs. Because even though data is becoming available in buildings, operators are expected to make sense out of that data based on their own expertise, based on their own training, and there is a lack of enough decision support tools out there to help the building operators take those decisions. Now, one of the challenges with data-driven techniques is that they tend to be opaque, and therefore naturally building operators do not trust them a whole lot. There's a lot of inertia from building operators in moving to something new, and especially something which is black box, when they have a lot of training and experience and trust on rule-based techniques. So traditionally buildings are operated based on rule-based techniques, which are mostly if-else type of constructs, and they are usually derived from some physics-based considerations combined with some heuristics. Now, one of the reasons why building operators behave in that conservative manner is because of this 330-300 rule, which states that the penalty of not meeting people's comfort needs is 100 times more than the penalty of not meeting energy sustainability goals. So to address this trust problem, some previous studies have proposed that there is a need to include building operators as part of the solution and technology development process. So include them as partners for technology penetration. Don't look at them as pure users of the technology. And that's where we feel visual analytics can play a key role. Another area of research, of work in this domain, which primarily appeals to the stakeholders belonging to the scientific community, is the area of machine learning model evaluation. Now, here is some results on machine learning applied to data from one of our buildings. And when we implemented various machine learning techniques and compared them with respect to a parameter or a metric, which is mean square error, we found that deep learning based techniques such as RNN outperformed the other techniques. So that is the conclusion we reached from just using the metrics. But then when we actually look at things in more detail, we see that the prediction from a deep learning based model doesn't capture the peaks, in the consumption profile very well. So that shows that just metric based analysis and coming to conclusions based on that is not adequate, and therefore there is need for further investigation, and that's where we believe visual analytics can again play a key role. Another set of problems in the buildings domain corresponds to this family of multi-criteria decision analytics. So the goal here is to essentially integrate operator feedback for real-time actionable and trustworthy inferences from the model predictions, right? So to explain this a little further, so what we are looking at here is we consider a multi-criteria decision-making problem where building operators ask questions such as, what happens to the building energy consumption if I change the room temperature set points? And then what is the corresponding impact on the occupant comfort? So they are essentially a variation of, or they are essentially a what-if variant of the prediction problems that were presented earlier. Now these problems are particularly challenging since any actions, any such actions are driven by multi-criteria operational goals. So for instance, minimizing energy consumption and also minimizing occupant discomfort, right? So these are two goals which are kind of competing with one another. Another set of competing pairs of goals would be maximizing grid services while also maximizing system reliability, right? So that these problems tend to be pretty complex. Now, to exemplify this problem, we look at a situation which corresponds to load curtailment, where the building operator curtails energy consumption as part of the grid service, right? So at the same time, they also need to make sure that the building occupants are not adversely impacted because of these actions. Now, this is a multi-criteria problem, since the performance is evaluated based on two competing criteria, that is the amount of the curtailed load and the occupant comfort. But then this is also a multi-decision making problem where the decision questions involve which or what appliances to curtail, what criteria needs to be prioritized, and so on. So the figure here shows this trade-off between these different decision choices across the competing performance criteria, right? So for example, if we increase the number of curtailed appliances to increase the grid service benefits that we see, we also see that this has a negative impact on the occupant comfort, right? So the trade-off point is pretty significant to address here. So the question is how visual analytics can help with this problem, right? So as we discussed, inferential reasoning of building predictive models for real-time decisions could often be very overwhelming, especially when the decisions have impacts on multiple performance criteria. And visual analytic techniques, in particular comparative visualization, can really help with these decision-making problems by improving explainability and also trust and transparency. So for instance, visual analytics can help in synthesizing and explaining the multi-criteria impacts of the decision choices, such as increasing set point temperatures or switching off lights, on curtailment and comfort. And also, the tools can help compare the impacts of relative priorities on multiple performance criteria to develop operators' trust on the model outputs. Right, so the trust point also is quite important here. So with that, we reach the we have kind of towards the end of our presentation. So to summarize, this is an overview of the visual analytic pipeline and how we believe that energy modelers and operators can kind of work together. So in my talk, what I did is I touched upon two aspects, right? I touched upon model calibration and model-based reasoning. So these are still just scratching the surface of the many possible ways in which visual analytics can offer adopting the best of both worlds, right? So the strength of predictive models for proactive control in energy systems, and also the need for reliable human-based decision making um, based on those predictions. So this kind of addresses both, brings in both the mathematicals or the system levels of sophistication, but also makes these techniques more practical, and therefore it kind of addresses the gap that we see between the state of the art and the state of the practice in this domain. So thank you for your attention, and then if you have any questions, please feel free to reach out to me or to my collaborator Aritra. Thank you again.